or negative work would be the work done by the gravity. Make sense?
Yeah. What is
So,
0, 0 again?
okay, so why is it 0, 0? We are assuming here that when you look in three-dimensional space, like in this silo, right? This vector is pointed straight down, right? That vector is pointed straight down. We're assuming gravity is straight down. The negative 200 is his weight plus the weight of his bag. Understand? Now, we know that in reality, it may not be completely straight down, depending on where you are on Earth, but for this problem, it's good enough, right? Okay. All right. Good? That's it. That's a pretty easy field, isn't it? That's a pretty easy field to work with. And I think most of you know from physics that you really only had to ever pay attention to his upward, that you didn't need to take into account any of this motion left and right. It's purely just the up and down opposing the force of gravity that matters. But we're going to see that in our formulation right here, aren't we? When we dot this with this, right? Because these first two components are 0, it's going to kill these two, right? Regardless of what they were. So it actually doesn't matter how he went up the silo. It's the fact that he got from the ground to 90, which is going to give you the force. Does that make sense? The left and right, front and back motion didn't matter. Just up. But do y'all see what I'm saying? I'm trying to get you to see that this shows you why it doesn't matter. Okay. All right, so I'm going to go back to this. This is, I know I'm going from 0 to 6 pi. I'm doing my force, right? My force with this curve plugged in, but my force doesn't have any variables, so I don't plug anything in. Dot that with 20, this one, negative 20 sine t. Did I say dot with that one? I think I did say dot with that one. I meant to point to this one. I'm sorry. The same thing, though. It kills off these pieces. So all you're left with is this. 20 cosine t 15 over pi dt. And what do you get? Negative. Ooh, negative 3,000 over pi. Right? I'm integrating that from 0 to 6 pi dt. And this just becomes negative 3,000 over pi t evaluated from 0 to 6 pi. Why is what?
Why is it 6 pi, the upper bound?
Wasn't t from 0 to 6 pi? Seen what?
We said 15 over pi t.
No, 15. It was 90 over 6 pi t was the z component of the curve. Then the derivative of that was the z component of the derivative. But then the t restriction was from 0 to 6 pi. Yeah? Okay, now we plug in and we get what? 6 in there to cancel. Negative 18,000 minus 0. And what would that be measured in? Well, because we're measuring the silo in feet and the man in pounds, this would be, work would be foot-pounds. So foot-pounds. Foot-pounds. That's the work. Sorry? I think it is. Yeah. All right. One more. I have enough time. I like this problem. There's going to be in the homework for this section, which I know all of you are going to do. They're going to have. There's quite a few word problems in this, or not word problems, but just more like this stuff towards the end. So just be prepared for that. A 10-kilogram object moves with a position function. R of t is sine 4t sine 8t t squared with t between 0 and 1. Find the work done on the object during this time period. Any ideas? Well, they want to know what work is, right? Okay, so we're going to need R, but we have it, and we're going to need R prime, right, to get our formula. So work is going to be integral, line integral, f dot dr like that. R is given to us by, like we didn't have to work for it, did we? It's there, it's provided. It's nice. I wish everything were free. I wish everything was just given, right? Okay, so you want the derivative? What's wrong?
You're like, I wish everything was free. I'm like, speaking of which,
Oh.
stop grades.
4 cosine 4t is the derivative of this, right? And then 8 cosine 8t is the derivative of that, and then this was 2t. So I'll need that in my formulation for this, right? Anyone notice something's missing here? The field, right? But like last time, what we did is, well, the man was 100 and something pounds, and we just said that the field was this thing. What's the difference between that and this? We have 10-kilogram object. That's his mass. So, or that's not his. It's an object. I don't know if it's a he or a she or if it's anything. It's 10 kilograms, right? It has mass. Mass is not a force, right? Mass is not a force. So right now, the field is still a question mark, isn't it? The field is still a question mark. I need a field, though. And for a field, I'd like to, since I'm talking about work, I'd like to see what the force vector is, right? So how can I get force if all I have is mass? So this is, again, some physics. Force equals mass times acceleration, right? Acceleration. Yes? You agree with that? But, if I have, when I say acceleration, it's the acceleration of the object. Not the acceleration of gravity, it's the acceleration of the object.
So we take the second derivative.
There you go. So look, if this is your position function, the first derivative is your velocity function, the second derivative is your acceleration function. So if I want to know what the acceleration of this object is, I take its second derivative. which is because this was velocity, right? So I take the second derivative, and I get negative 16 sine 4t. And then I do derivative of this, and I get negative 64 sine 8t. And then derivative of this, I get 2. That's your acceleration function. Then if I want the force as a field, it's the mass times the acceleration function, which is going to be, well, mass is 10, right? Multiply this by 10, it's a scalar. So you get negative 160 sine 4t, negative 640 sine 8t, and then 20. Yeah? There's your force. Pardon me?
Could you just pull the mass right at the end?
Yes, you could have taken the mass out of the whole thing. But if it was not given, like if they said the mass of an object is m, you would want to pull that out. If it's 10, then you may as well keep it in. But you can take it out. It doesn't matter. All right, so all I need to do is dot these. What dot these? I said these. What do I mean? I need to dot my force with r prime. But what? Good question. Don't you need to plug in the r into this? Well, this is already in terms of t, so we don't need to do that. It actually came from that, right? But so we're good. We just dot those two together.
Yeah, that's why I said go ahead.
Do we have a restriction on t? It was given, right? 0 to 1. Dot, dot, dot. Here we go. So this times this. So negative 160 sine squared 4t. Right? Oh, I'm sorry. Who? I don't know why I pointed up there. This times this. Negative 640. Is that right? 640. Sine 4t. Cosine 4t. Y'all good with that? Here and here. Then I got to go here and here. Maybe we should have pulled that 10 out. What is this going to be?
Negative 5,120.
Negative 5,120. Sine 8t. Cosine 8t. And then finally, 20. That one I don't mind doing. 40t. And then dt. How are you going to handle this right here? Sine 4t, cosine 4t. Double angle formula, turn that into what? Sine of 8t, but half of that? So scale to 640. I hope everyone's comfortable with that. These are those little things that I do that I just don't know. I remember as a student like not knowing how the teacher did something, and here I am doing the same thing. This is negative 320, what, sine 8t. Okay, I'm going to have to stop. Negative 320 times 2 sine 4t cosine 4t. That's this right here, right? Nope, not distributed. Then this, using the formula, is sine 8t. So go back and look at your double angle formula. Sine 2u equals 2 sine u cosine u. So that's your double angle formula, but replace that with 8t. And then this one, same thing, right? I can do the same on that. So minus, what's half of that? 2560 sine 16t. And lastly, 40t. I don't have to change that. And then I get to integrate. Am I out of time? No? Okay. So we get to integrate. Go ahead and integrate that. I'm wondering if I took this problem out of the book. I thought maybe I had taken this problem out of the book, but I don't see it in here. All right, well, it is what it is. Yo, what did you get? You got a final answer?
Yeah. Well, I mean.
What did you get?
For the integration or for the?
Like everything?
Oh.
No? I thought you were saying you got everything. Y'all think y'all could do that from there?
Oh yeah.
Okay. All right. You get the idea, hopefully. All right. So just so you know, last night I was going to grade your test, honestly, the ones you had turned in. I sat down, and that's when that hailstorm came in and just ruined my night. And so I don't have those for you. The ones you just turned in today, I've got to grade those also. But I'm giving 2 exams tomorrow for my Cal 2 and for my college algebra. I promised them I'd have their tests graded by Friday so that they could drop if they needed to. So that basically what I'm telling you is that I'm not going to get to yours until this weekend. My intention is to have both your mini exams back to you Monday, and then I'll give you your new one. I believe the new one will be the last one. All right? We're good? We start 13-3 next time. We're doing good time-wise, I think.
So we made up for that one day.
I don't know if we made up. All I know is we have 1, 2, 3, 4, 5, 6, 7 more sections, and I think we have more days than sections
We
still.
have 4 more, right? 4 more days.
Till the end of the semester?
Without the phone.
Is it 4? No, it can't be 4.
Or it's just 2.
I hope it's 6.
I thought.
We don't have 2 more weeks left. Is that right?
I thought this was. I thought we have 2 more weeks left.
Hold on a second, man. When's our last day?
It's May 13th, I think.
It's early, man.
No, it's not. That's late. We have the 18th, the 20th, the 25th, the 27th, the 2nd, and the 4th, and that's it. So we have 6 more meetings,
We have 6 more meetings?
6 more class meetings, and then the final is the week after that. No. Well, we're not. I'm saying I have 7 sections to cover in 6 days.
Oh, okay.
It's going to be tight. It's going to be real tight. Live streaming, yeah.
Oh, hey, you know.
I usually just barely am able to touch the last section. But the last section's really clean. It's just like, here's a formula. Boom. Like we get to a final result and it's good.
You know that girl in our district, the tall one? Yeah. She's gonna do this.